Hello everyone, myself is Sunil Kumar Srivastava, working as a teaching assistant in Biotechnology Department of Institute of Engineering, Bundelkhand University, Jhansi, and my subject here I am teaching the subject Thermodynamics to the second year of this your Biotech department. So, I would like to have some lectures on my topic second law of thermodynamics. Thermodynamics is concerned, it is having two statements. It consists of mainly two statements. One is your Kelvin Planck statement, and second is the second law of thermodynamics. It consists of mainly two statements. One is Kelvin Planck statement, and second is Clausius statement. So, according to the first statement, this statement tells that it is impossible to construct a machine which purpose is only to convert energy as heat completely into the work, that we cannot completely convert heat into the work. Some losses will be there all the times. That is the first statement, and according to the second statement, it is impossible, quite impossible to have any process which to transfer the energy from low temperature to higher temperature. It is not possible. So, these are it consists of these two statements. Now, according to this second law, some equipments are there. One is your heat engine, then other one is your heat pump. So, as far as heat engine is concerned, in the heat engine what happens, that we are taking the some amount of heat from the high temperature reservoir, and that heat is given to the engine. So, that engine is taking the work from that heat is input for that engine, and we are that is converting some that heat input heat into the work. So, some amount of work we are extracting from that heat. Then whatever the rest heat is there, that is rejected to the low temperature reservoir. So, we are rejecting at the low temperature reservoir. So, in this case, in heat engine, our efficiency will be heat input, the work done, that is the output, work done is output, that divided by input. So, efficiency will be efficiency of heat engine, that will be equal to work output divided by input. So, this efficiency of heat engine, this will be work output. Here is it is the work is W. So, W is the difference of two heats. One is heat input, which is Q 1, other one is heat output, which is Q 2. So, Q 1 minus Q 2 will be the work, that divided by input. So, Q 1, or we can say this is W upon Q 1. We can also write it as Q 1 upon Q 1 minus Q 2 upon Q 1. So, this is equal to 1 minus Q 2 upon Q 1. So, this will be the efficiency of the heat engine. So, here what we are doing, that we are extracting the heat from the high temperature reservoir. We are taking the heat from the high temperature reservoir, but in the case of heat pump, what happens, that we take out the heat from the low temperature reservoir, and then we are giving some work to that system. In the heat engine, we are taking some work from the system, but in the heat pump we are giving some work to the system, and finally, we are rejecting the heat at the higher temperature. So, it is somewhat we can say it is the reverse of the heat engine. In a heat engine, your input is taken from high temperature reservoir. In the heat pump, the input has been taken from low temperature reservoir. So, and the rate of work or whatever the performance of the work is there, that will be given by the coefficient of performance by the heat pump. So, that is another term. So, for heat engine, the term is the efficiency, for measuring the efficiency, for measurement of the output, that how much efficient it is, we can have this way. Now, one thing is also there, this 1 minus q 2 1 by q 1, this is also equal to 1 minus T 2 upon T 1. That means, the temperatures we can write at the place of q 2 and q 1, the T 2 and T 1. T 2 is the lower temperature, at which we have thrown the heat at the low temperature reservoir. T 1 is the higher temperature. So, this ratio of T 2 by T 1, that comes equal to q 2 by q 1. So, that way we also can find out the efficiency. Now, in the case of this heat pump, we will put a term COP, that is your, that we say, that is your for heat pump, we take out COP, HP, we write this. This is called coefficient of performance. Now, for this COP or for this heat pump, we can use this atmosphere. This atmosphere works sometimes as a high temperature reservoir and sometimes as the low temperature reservoir. As in the case of high temperature reservoir, whenever you have to do any space heating, that for that space heating, this your atmosphere, it is working as the low temperature reservoir. If you want to work as a refrigeration purpose, then this atmosphere, it will work as a high temperature reservoir. Okay. So, this way one thing is also left here, that is which is very popular as nowadays, this that is also a heat engine, which we say as a Carnot engine. Carnot is the engine is the most efficient engine, which is among two temperatures. No engine can be more efficient than the Carnot engine, and in the Carnot engine there are 4 steps are there. For that is a Carnot cycle, we can say that Carnot cycle on the Carnot engine is working on the Carnot cycle, and in this Carnot cycle there are the 4 steps are there. First 2 steps are compression steps, then another 2 steps are of first 2 steps are expansion steps and another 2 steps are compression steps. So, in the among the first 2 steps, initially the gas is expanded isothermally and reversibly, and it is temperature is at a high temperature reservoir. This is the Carnot engine. So, this engine is mainly based on Carnot cycle. There are 4 steps here, I will show you by this diagram. If we plot it by the PV diagram, then what happens that there are 4 steps. We are starting from the state 1, okay. We are going to state 2, then again we are going to state 3, then we are going to state 4, then finally 4 to 1. So, 4 steps are there, 1 to 2, then 2 to 3, then 3 to 4 and 4 to 1. So, we are coming to the same 1.1. So, that means that we are moving in a cycle, as we are starting from 1 and again we are coming to 1. So, this is a cycle. So, this is a Carnot cycle. In Carnot cycle are these two steps, number 1 to 2 and 2 to 3. These both steps are isothermal expansion. Now, whatever the gas is there in the cylinder, that gas is expanded isothermally and reversibly in the 1 to 2 step, and here in the 1 to 2 step the temperature of the gas becomes T h, that means it is at the temperature, or we can say this is at the temperature T 1. Initially it is taken at the temperature T 1, in the 1 to 2 step it is the temperature is T 1, but no temperature changes there, it is in contact with T 1, but no temperature because it is an isothermal process. In the second 2 3 this is also isothermal process, and but here also compression is there, but your temperature remains same also here, but in this in the other step two other steps 3 to 4 and 4 to 1. These two steps are adiabatic compression. So, in these steps, two steps, our no heat loss is there, no heat interaction is there, only gas is compressed reversibly. In these two steps 3 to 4 and 4 to 1, the gas is taken to the initial state up to the final state 1, and its temperature becomes the T 2, that means initially it was T 1, then the heat is rejected at temperature T 2. So, this way it makes a complete cycle, which is your Carnot cycle, and this Carnot cycle the engine which is working on the Carnot cycle, that is the most efficient engine. No engine can work more efficiently than the Carnot engine.